Hello, hello, hello again, my physics friends, on this Sunday, April afternoon. I am very excited to share this problem with you. I find it really fun, and it's something that would, I think, be kind of challenging to do at the intro mechanics level, but with our new way of thinking about Newton's second law and our way of thinking about the momentum conservation and what a system is, and the fact that in the absence of external forces, the momentum of the system must be conserved. I want us to think through this problem, and here we go. So let's consider the following problem. We have a satellite of mass m traveling at velocity v. So let me bring in something that looks like a little satellite. I don't know why I drew it as a hexagonal shape, but there we go. And we're told that it's moving at some velocity, which we'll label v. Here I've just drawn it straight to the right. We're told that the satellite is bombarded by dust particles that collide and stick to the satellite at a rate of dm dt. We're also told that the dust has a velocity u just before it hits. And we're asked, what force in both direction and magnitude must we apply to the satellite in order to keep the velocity of the satellite constant? And we want to know both the speed, we want to keep both the speed and direction of the satellite's motion constant. Okay, so let me start here by annotating this diagram and drawing in some dust that's coming in with velocity u, and I don't know, we can have some, how about some blue dust coming in? Okay, so we have this kind of parade of dust particles that are coming in. It's not a single particle, but rather it's almost like a river of these particles coming in, and we're told that the velocity of all of these particles individually is u. And I've drawn it here down and to the right, but it could be in any direction. For generality, though, we don't want u and v to be in the same line, because that would be a special case of this more general case. Okay, so the question here is, what force must we apply to the satellite in order to keep its velocity constant? Okay, so let's imagine that we have kind of the power, we have some kind of finger of God, if you like, or we're able to reach up and force the satellite externally. What direction and what magnitude of force should we apply? So here I have my little arrow. I don't know yet what direction I should apply and how large that force should be, but I want to figure that out. Okay, let's start, before we do any calculations, okay, let's talk through some of the key ideas here. And in particular, let's start with a simpler case where instead of a stream of dust particles, we just have one massive object that hits and sticks to the satellite. Okay, so let's consider a simpler case. And that simpler case would be, we're going to take the satellite, but instead of having a stream of dust particles, we'll just have one object of mass little m hitting our satellite. In this case, if we have these two objects, and if we first define our system, and define our system to be the collection of both of these objects, okay, so our system is satellite and projectile, then we can say something about the momentum of the system before and the momentum of the system after the collision. So let's do that. So here we have the momentum before the collision is the momentum of the dust plus the momentum of the satellite. And the momentum of the dust is going to be parallel to the dust velocity, and the momentum of the satellite is going to be parallel to the satellite's velocity. The momentum of the dust is just its mass, little m. Oops, why is that red? I don't know. We got to undo that. It's going to be the mass of the dust times its velocity u, plus we're going to have the mass of the satellite times its velocity v. But notice u and v are not parallel. This is a full vector equation, okay? And so this direction p dust plus p satellite is not going to be to the right, and it's not going to be parallel to the dust, but it's going to be a combination of the two. So if we assume that big M and big V are much bigger than little m and u, then we can kind of redraw the satellite's velocity in a more representative way. It's probably going to be a longer momentum, something like that. So this p before is going to be the satellite's momentum, and then we're going to add to it the dust's momentum, and the resulting momentum will be the system's momentum before, which maybe we'll just call it P before. That's what we called it in the equation. Okay, so P before is not to the right and it's not parallel to the dust, but it's a combination of the two by vector addition. And if you don't do anything, if you just let the collision happen, then if there's no external force, P after will also be along that same line. So we can show this here. After the collision, we have the projectile, in this case, a big chunk of something, dust or otherwise, is now attached to the satellite. And if there are no external forces, which is what we're starting with as an assumption, then the before and after momentum have to be the same. Okay, and now there's only really one object at play here, so that tells us that the velocity vector in the absence of external forces is going to point down and to the right. It's not going to be to the right. It's not going to be parallel to the initial velocity because now we have this downward component. And furthermore, we know that the final velocity is parallel to the final momentum. Right, that's by definition because the final momentum is the total mass of the system multiplied by the velocity after the collision. So those two vectors are parallel. Okay, so we can see right away that we're going to need an external force in order to compensate for this downward velocity if we want to maintain the original velocity. Number one, the direction has to be changed. Number two, we may also need to change the length of this vector. Okay, so how do we determine which direction that we need to point? To answer that question, we're going to do that in the context of the full problem. And I think we're ready to move on to that because we've developed some intuition for the problem using the simpler case of two particles colliding and sticking together. So let's come back to the original problem and think about how we're going to talk about a flow of mass at a given rate, dm dt, as opposed to a single particle moving at a velocity u. So here we are back at the original problem, and notice we have to think about how to deal with this mass flow onto the satellite. I'm going to draw the kind of end result that we want, which is the satellite plus the accumulated dust moving to the right with the same velocity vector. So let's map that out. So in particular, we have the first diagram is the system at time t, and then the second diagram would be the system sometime later, t plus dt. So system, what is the system? We have to select it, and we have to make sure that we don't change the mass of the system. If we're going to talk about momentum conservation, we need to talk about the momentum of all of the objects in our system before and after. So I'm going to draw a diagram, a little circle here, and I'm going to include in my system the satellite, of course, and I'm going to select some of those dust particles, okay? So notice I'm including these clustered dust particles, but I'm not including those other dust particles, okay? So after the collision, I'm going to make the statement that all of the dust particles that were in that green boundary are now attached. They're stuck to my satellite. So there's 3, 4, 5, 6, 7, about 7 of them. Okay, so those ones have attached. And so now this is my system. It's a satellite plus just a few of those dust particles. The other dust particles have come closer, but they're not yet collided with my satellite. So let's draw that. So I'm just going to duplicate my dust particles and take a copy, but notice these are only the dust particles outside of the boundary, and I'm going to bring them, so now they've approached the satellite, they're closer, but they are not yet across that boundary, okay? So before the collision, I have satellite plus these 6 or 7 dust particles. After the collision, I still have those 6 or 7 dust particles and my satellite, and I'm not including any of the other particles yet. Okay, so how do we write all of this down then? So I'm going to define a little increment of mass, dm, and I'm going to call that the mass of the dust that will hit the satellite in time dt. So it's the amount of dust that's defined to be within my system. So let me draw this. if I add up all of the mass of those dust particles, I get a mass dm. So now I can write down my momentum of my system before the collision. In other words, what is the momentum of the system at time t? Okay, and that's going to include the satellite and its velocity, but it's also going to include that little amount of dust times its velocity. And then, after the collision of those dust particles, I have my p sys after, that's the system's momentum sometime later, t plus dt. I'm going to have all of that mass of the satellite plus the dust now by assumption is moving to the right at velocity v. But of course, in order for this to happen, I must apply some external force to this system. Otherwise, as we saw in the previous example, the momentum would not be to the right. So I'm assuming here there's some external force on the system. Okay, and we're going to be applying this constant external force. And our goal is to use momentum conservation to figure out what is the magnitude and direction of this external force such that the satellite continues to move to the right at velocity v. So this is where we transition to Newton's second law, which says that the change in momentum of the system is brought about by an impulse. Okay, and this is a change in momentum over a very short time is brought about by an impulse over that same short time. Well, we know just the definition of dp is the momentum in the second state minus the momentum in the first state. Here our first state is the time t and our second state is the time t plus dt, so we're going to take the difference of those momenta. But we already have expressions for each of those two momenta. The second momentum and the first momentum are already defined, so we can bring that into the left-hand side. And then we can see that we can distribute through the v to the m and dm, and we're going to get some cancellation. So let's see that in action. We bring that over. We have two terms, mv and minus mv, so those are going to cancel. And then we'll have a dmv and a dmu with opposite sign. So we can factor out that dm to simplify the problem, and we'll bring down the right-hand side unchanged, f external dt. And remember, we're trying to find what is this external force that we need to apply such that the velocity is constant. So we just solve for f external, and we find the following expression. The external force depends on the difference of v and u, and it depends on the mass rate incident, the mass flow of the dust. What is the rate of mass increase of the satellite? So first of all, you can see if there is a very high mass flow, dm dt is large, we're going to need a large force in magnitude to compensate. That makes sense. And also, we had a question when we did the simplified problem of whether this external force is going to point to the left or to the right, in addition to having the upward component. Now we can see how we're going to answer that. We have this v minus u, which is the difference between the satellite's velocity and the dust's initial velocity. And we see that the difference of those two velocities will give us information about the direction of this external force. So I want to take a few minutes to talk through different scenarios for v and u in terms of their relative size and their relative direction to figure out what direction this external force must point. Now let's start with v and u as we drew it in the diagram at top left. Okay, we had v pointing to the right, like that, and we had u coming down and to the right, like that. Okay, well, v minus u is v plus negative u. So if we make a negative u vector, like so, and we add that to v, or if you like, you can do tip to tip for vector subtraction, but it's the same. We have v minus u. So we know f net has to be proportional to that blue vector, has to point actually up and to the right. So we understand the up component because that's counteracting the downward momentum of the dust. And now we have this rightward component, which comes about because of the relative sizes of v and u. But here's another way to think about it. you could have the u vector tacked on to the end of the v vector, and it could sweep out kind of a circle, and the tip of that circle represents all the possible places where f net would end. So let me draw that out more directly. So I have my v vector, and I have my minus u vector. And this is the minus u vector as drawn in the original picture, but I could have drawn my u vector in any direction, down and to the right. I could have drawn it straight to the right, straight to the left, straight up or straight down. And I could tack on that minus u vector to the end of my v vector, and if I only change the direction, then the tip of that minus u vector will sweep out a circle. And my net force, F net, has to start here, and it's got to end up somewhere on this circle. So for example, if I let my minus u vector point this way, for example, then my F net is going to point like this. But no matter how I orient the direction of my dust velocity, as long as the magnitude of the dust's velocity is smaller than the magnitude of the satellite's velocity, then all of these points on the circle are going to be to the right. So my F net will have a rightward component. If, however, I let the speed of my dust be faster than the speed of my satellite, then I can get my u vector to point leftward of the v vector. So let's look at that example. So in that case, we will see a short velocity for the satellite, and a larger speed, or short magnitude a small magnitude for the satellite, and a larger magnitude for the dust. And we're going to get a circle of radius u's magnitude. And now we can see that the net force could point in any one of these directions. It could point up and to the right, it could point backwards, it could point down and to the left, it could point down and to the right. As long as it starts where the velocity vector starts and ends anywhere on that circle, the F net vector could point in any direction. Okay, so we've kind of talked through qualitatively the direction of F net, but let's do 3 specific cases for u and v. We'll do u is equal to v, u is equal to minus v, and u is perpendicular to v. So we'll start that on a blank page. So here we go. We'll say for case 1, and we'll do these 3 cases, we'll say the dust moves parallel to the satellite, and they have the same direction and magnitude. Okay, so in that case we have our satellite like so, and we have our dust like so, and the satellite is moving to the right, and so is the dust, and they're moving to the right with the same speed. Well, this equation that governs the external force we have to apply says the force is proportional to v minus u, but if v is equal to u, we don't have to apply any force. Well, does that make sense? Yes, it does, for the following reason. If the dust and the satellite are moving at the same speed, then the dust will never hit the satellite. So there's no need to apply any external force because the mass of the satellite is not evolving in time. There's no collision to speak of. So here, F net is equal to 0. Sorry, I call it F external is equal to 0. We do not have to push to keep the satellite moving as it was moving before. There's nothing that's trying to change the motion of the satellite. Okay, so that case is pretty straightforward. How about case 2? This time let's let the dust have the same speed, but opposite direction from the satellite. So this looks like the following. We have our satellite moving rightward with velocity v, and our dust leftward with velocity u, and those 2 speeds are the same. So according to our equation, for the force we have to apply, we'll see that we need an external force that's equal to v minus u times dm dt. And here, if u is minus v, then this ends up being 2v dm dt. It's v minus v, or plus 2v. And so this tells us we have to push to the right with an external force. Okay, so I need to apply an external force to my satellite that's rightward, parallel to my velocity. And so, yeah, I see the external force must be parallel to v. And why does it have to be, why is it proportional to 2v? Well, two things are happening. Number one, I have to change the direction of the dust. What do I mean by that? Well, initially the dust is moving to the left. After it sticks to the satellite, I want it moving to the right. So I essentially have to bring the dust to rest and then accelerate it to the right. So I have to take its momentum that was once leftward, and I have to convert that to a rightward momentum. So that's twice as much of a momentum change as just bringing the dust to rest. And so, well, that's, I guess, the main point. I called it point 1 and point 2, but we basically have dust momentum was dm to the left initially, and then we want it to be dm to the right in the final state. So that's a change of momentum of 2 times v times dm. Okay, that's case 2. And then for case 3, let's consider the case where the dust is moving perpendicular to the satellite's velocity. So here we are showing the satellite moving to the right and the dust moving perpendicular to that downward. And let's be really explicit here. Let's draw out a coordinate system. Let's call the rightward direction the x-hat vector direction and the vertical direction the y-hat direction. In that case, we can write explicitly the velocity as a speed in the plus x-hat direction and the dust velocity as a speed in the minus y-hat direction. Okay, and so let's use our derived equation to write down the external force that's required on this system in order to make the velocity, in order to maintain a constant velocity for the satellite. So we need this external force to be v minus u dm dt, which is, so we need to know what is v minus u. Okay, well, let's do that. V we can write as, not that, we can write it as a speed in the x direction, nothing in the y direction. U we can write as nothing in the x direction and minus u in the y direction. So therefore v minus u will be v in the x direction and plus u in the y direction. So we have our external force would be v x hat plus u y hat times dm dt. Or if we want shorthand notation, we could say v u dm dt. Okay, so we see in this case, we have a upward and rightward force that we must apply. So we can draw this out here. We have to apply a force, this external force, and this external force has an upward and a rightward component. The rightward component is v dm dt, and the upward component is u dm dt. And we can say a few words about how to interpret the values v dm dt and u dm dt. The vertical component being u dm dt, we can think of as the vertical component of the force is bringing the dust to rest. In other words, if we apply a force u dm dt, we can bring, for a time interval dt, then that provides an impulse u dm, and that impulse u dm will bring a certain amount of dust to rest in the vertical direction so that it can travel with the satellite to the right. We need this horizontal component v dm dt. We need that force because the effective mass of the satellite is growing. It's equal then to, the original mass of the satellite plus an amount of extra dust mass, dm, and we have to apply a force to accelerate that extra dust mass to the right, because originally the dust has no horizontal velocity. It only has a vertical velocity. So the vertical component of the force brings the dust to rest, and the horizontal component of the force accelerates that dust to the right. And at the end of the day, once you've applied both of those components, or in other words, once you apply a force up and to the right, the satellite plus the extra dust will be moving rightward with the same speed that it started with. So my hope is that with this video, you've gotten a little bit of exposure into how to use and think about problems in which the mass is changing at some rate, as opposed to a single particle coming in and colliding and sticking. And we have this kind of idea of a momentum flow, or a rate at which a mass of an object will increase. And if we think about Newton's second law in the differential form that we talked about before, that the change of the system's momentum over a short time interval must be brought about by an impulse over that small interval, where the impulse is an external force applied for some time interval, then that allows us to think of situations in which the the mass of an object might be changing at some rate, as opposed to just once from a single collision. Cool. Well, hopefully you enjoyed this, and it gives you some insight into more complicated problems dealing with momentum. And until next time, take care and be well.